So for the last part of this question, we're interested in finding the total runtime now of the Dijkstra algorithm using the hash map implementation. So actually, parts A and B have done the majority of the work for us. Now it's just a matter of combining those answers. So remember, part A determined how many times we call each of these operations, and part B determined the runtime of a single call to each operation using this hash map implementation. So to get the total runtime, right, part C, that's really just a matter of multiplying these together, right? Okay, so basically for in Q, I have O of V times O of 1, which is going to be O of V, plus, okay, I'm doing all these operations, so I need to add on to my runtime. So for DQ, I have O of V times O of V, which is going to be O of V squared, plus is empty is going to be total of O of V, contains key is going to be a total of O of E, and update is also going to be O of V. So now that I have these runtimes, it's just a matter of simplifying. So remember that for runtimes, we can always just simplify it down to the most significant terms, right? So V is smaller than V squared, and so really I can just ignore all of these O of V terms. So what I have left is O of V plus 2E, right? And remember that we can ignore any constant factors, and so that really just becomes O of V squared plus E. Okay, so now here's the tricky part. So remember that the maximum number of edges you can have in any graph is an order of V squared, okay? And the minimum number of edges you can have is an order of V. And so let me explain why. So my claim is that E is going to equal V minus 1 in the minimum number of edges case. Okay? And the reason for this is because if we want our graph to still be connected, but want to have the minimum number of edges, right, we cannot afford to have any redundant edges. What I mean by redundant edges is if I have a path from a vertex A to vertex B, for example, right, through some other vertices potentially, I cannot have another path from A to B, right? Because I already have a path from A to B. So if I have another path from A to B, that's wasting edges. Okay, so in other words, if these are undirected, let's just for simplicity imagine that these are undirected edges. In other words, I cannot have cycles. All right, if I have a cycle in my graph, then that means that I'm wasting edges. Okay, so what is a connected and acyclic graph called? This is equal to a tree. Okay, and in a tree, the number of edges is always exactly equal to the number of vertices minus 1. All right, now what is the maximum number of edges I can have? Max number is, for a directed graph, it's going to be V times V minus 1. For an undirected graph, so this is for directed, and then for an undirected graph, it's going to be that same quantity, but now divided by 2. And let me explain why. So for a directed graph, right, let me just give you a really small example. So let's say I have A and B, okay? So the maximum number of edges I can have between these two nodes in a directed graph is I can have one going from A to B. I can also have another one going from B to A. These are two different vertices, right? Remember, AB is not the same thing as BA, where this tuple representation denotes an ordered set of edges. Okay, in this case, we have an ordered set of edges precisely because each edge has a direction associated with it. All right, so if this is the case, then I can generalize this to perhaps 3 vertices. So I can have A to C, I can have A to B for my vertex A. For my vertex B, I can have an edge from B to C, and an edge from B to A. And then for my vertex C, I can have one from C to B and from C to A. So what was a pattern here? For every vertex in my graph, I could draw an edge to every other vertex, every remaining vertex in my graph. So if I have a total of V vertices, right, for each of them, I can draw an edge to a total of V minus 1 vertices. That means I just need to multiply these quantities, and that's exactly what I get here. Now what about the undirected case? Remember that for an undirected graph, these two edges are exactly the same. So here, AB, an edge going from A to B, is exactly the same as an edge going from B to A. In other words, for every two edges, right, that go between the same pair of vertices, I only count them as one. Okay, so that means that I half my count. So that's equal to the previous quantity divided by 2, right? So either way, E is going to be an order of V squared. Okay, for the maximum number of edges. So if E ranges from O of V to O of V squared, right? Then basically I can simplify this expression to be V squared plus, in the worst case scenario, V squared, okay? Which is equal to O of 2V squared, which is just equal to O of V squared. And that's the answer.